Then the modeling is what? Modeling is you model a system, you model the relationship between force and position. You're modeling the temperature and the airflow by equations. So you have those differential equations to represent. You have those differential equations to represent your dynamic systems. So in order to further elaborate, okay, basically you have differential equation. You want to know exactly what the character equation between the two are. You want to find out a function where your variable is input, then you get your function value. Right? That is the best thing. That means if I know the time, I know my position. If I know the time, I know my temperature. If I know the time, I know the speed. But most of the time, it will be very difficult for you to solve differential equations, especially when the differential equation becomes even higher. So in dynamics and control, you can use differential equations to represent dynamics. Basically, you want to have certain control. Okay, to control the performance, you want to further elaborate the and usually there are two ways. One is to call the classic control. Classic control, what it means? They use some mathematical flow, which is called Laplace. So you see this one, they use the Laplace transform. So basically, your Laplace transform basically is to transform your differential equations into polynomial functions. Then, if, for example, you have a second order differential equation, then you convert to a second order polynomial function. Then it will be much easier for you to solve the polynomial function rather than differential equation. Okay? This is something called the classic control. And the other one is something we are doing now is the model control. So basically, they convert the differential equation, high order differential equation to state space. And what is state space? State space, the tricky part is they convert your high order differential equation into a higher rank of equations. But for the equation, it's only first order. If you notice your state space, your equation, if you talk about differentiation, always the first order. Right? It's the first order only. So it's the first order, then plus some of the constants. So you have a first order, you have a certain relationship between your so your state is basically is a first order equation. Okay, by how that is represented by a certain linear combination. So the tricky part for the state space, if you have a nth order, for example, if you have a second order, okay, differential equation, you can convert by two matrices or your order or your rank of two for vectors, right? Your state vectors. Then you go to a second order by two state space. Then you use the by two state space together with the first order differential equation, then the second order equation. So if you have nth order differential equation, by using the state space, your differential order will be 1. Your state space will be 2. Okay, that's like that. So basically, the purpose, no matter you talk about the state space or the Laplace, they just want to simplify your differential equation. They want to lower down the rank of your differential equation. For the Laplace, is through the Laplace transform, convert your high order differential equation to a high order polynomial function. Then after you solve the polynomial function, you are able to use the inverse Laplace. Then basically, no matter whether you talk about the state space or you talk about the Laplace transform, basically they are mathematical tools for you to understand the characteristics of your differential equations. And for the Laplace transform, after you get the S function, basically you have the denominator and denominator, right? And usually you will present this one after factorization. You will get this one in the 0 and 4. So you know the zeros, you know the especially the very important for the location, right? And this one becomes your link to your performance, right? To your system performance. The location of the poles have something to do with your tension response, have something related with your state, right? So this is the main purpose for the Laplace transform. So basically for the dynamics, the purpose for the Laplace transform is to simplify your high order differential And look at the control process. After you convert to the Laplace transform, you get your second order or your other orders polynomial function as a function. You not necessarily solve. You not necessarily solve your differential equation. You not necessarily know exactly what the function is y b, your position, right? But now you know your transform function. Through the theorem for analysis, you are able to distinguish possibility. You are able to determine how to do. So this is some tricky part. Some tricky part. You are not necessarily to solve the function, right? But through the poles, through the rule of pi, you are able to achieve a good design of your controller. And later on, they also review about certain type of the traditional input, including the step, ramp, sign. If you pay attention last week, or the week before last week, you also study similar things in the literature part, right? So in your dynamics part, you have learned how the input, like the impulse, your unit step, your ramp, your sign, cosine, condition functions, alright? Later in the different control, you also learn the right? Like you notice, their representation is slightly different. Okay? Then they also review the so-called final value theorem. And please pay attention to the condition. This one, this theorem is true. You must make sure the condition here is the system is stable. If your system is stable, then you have a constant or you have a converge final state. Then you have this one has a certain meaning plus final value. If your system is not stable, it means no final value at all. No final value, how can you apply the final value? The later we also review about the block diagram. Similarly, in the teacher control, you are also after you obtain the dash transform function, you are also able to use the similar. And in the continuous control, the impulse response is very important, right? So the impulse response are linked between the signal and system, right? So your output signal of the impulse response can describe your system model. Because the Laplace transform of the impulse function is 1. Similarly, later in the digital part, we also learn something about the unit impulse. Right? And the unit impulse, the good thing is, if you have a unit impulse input, the unit impulse response signal will represent your digital process. Right? And the tricky part is, for the Laplace transform, your impulse function Laplace transform is 1. And in the digital control, the Z transform of your unit impulse, right? And for the analytical part, you also review a typical first order and second order system, right? Because I believe in your dynamics control, you need to cover first order, right? And how to handle higher order? Most likely you are going to use fractionalization, right? Basically, the tricky part for math is as long as you know how to solve first and second order. If you got third order, how you do? Most likely you can come certain factorizations, right? Then your third order becomes a combination of your first and second order. So you can bring that back most of the time. Then sometimes they are not able to bring that, then the most likely is already in certain like K power 3 or K power 4. Also not so so the tricky part is you need to understand where about the first order and second order. So for the first order you have a stability, you also have a time constant. Okay. Maybe you may not pay much attention on the stability, but for the stability of this first order, what is the condition to stability? What is the condition for this system to be stable? The condition for this one to be stable, your sigma must be a positive value, right? Then your root will be a negative value. Then your explanation function here is a negative value at your power minus, right? Your sigma must be positive, then minus sigma becomes negative. Once your power is empty, then this one will be negative. Otherwise, you will diverge, okay, and become unstable. So the stability for the first order is very simple. Okay, the root must be negative, or your sigma must be positive. And also, you can also do the analysis about second order. So for the second order, you have your natural frequency and the damping region, right? So after you get your general flow of your second order, and you notice actually why do you want to represent this one in the sigma and the omega t, rather than just use the natural frequency and damping region? Because this sigma and the omega t represent where the pole is, right? So actually your pole S12 is basically your minus sigma plus minus j omega t, right? So if you know your sigma, you know where is your horizontal, and if you know your omega t, then you know where is your imaginary part, right? So this is something I want to highlight. Okay, you need to understand what this figure means. Okay, this figure join this one for you, tell you. Okay, your root location minus the real part is minus sigma. The positive side is plus or minus omega t. And if your sigma is positive, or your root is minus sigma, which is on the negative side, then your system will be stable, right? Then so will take it out. So once your system is stable, one way you can use the impulse response, right? To check how is your system's stability. And if your system is stable, then you can also further elaborate about the unit step. So you can see what the difference between your unit step and your impulse. Unit step. And this is your impulse. So which one determines the stability? Is this sigma, right? Is this part. Is this one where the damping is 0? Then your impulse will negate to 0, right? Then your system is stable. Then your impulse response eventually will negate to 0. And if this one will negate to 0, then your unit step will converge to the unit step. Okay? So through this, you should understand what the stability really means. Okay? Rather than just remember by hand and by. And this is something I think we have highlighted in class already. So this is basically their lecture notes on the end of review. Okay, then we come to the stage, so-called introduction to the digital control. So the introduction to digital control actually there are two parts. One is talk about the signal, right from the system. So this is a traditional analog digital group in control system, which is very familiar. Then the difference between the digital and the analog is we got certain differences. First of all is the signal. Your input signal instead of analog. This one you input sampling, you have analog digital converter. Then your input signal becomes. Then at your control part, instead of differential equation, you have your difference equation. Instead of Laplace transform, you have your transform. So your controller becomes digital controller. What do we mean by digital controller? Digital controller means you are going to use difference equations rather than differential equations. You are going to use immutations rather than using equations. So this is something we spend about 2 chapters later, right? About the difference equations, about their functions. And after you get your output by your digital controller, your output itself is a digital signal, right? Then the third part we need to learn in the digital control part is how to convert your digital output signal to your analog signal. Because eventually your real physics will still analog signal, right? We can use digital system to deal with our control here, our computing, deal with our information system. But the real basic words are always continuous, always right. So basically through this graph, I hope now today that's when we review this, when we learn this, we understand what the meaning of this. Before the exam, you don't need to look at anything, just look at this picture. You should be able to recapture what this picture. Okay? So basically these are the three parts we have done so far, right? So week 2 we spent about 1 week about the sampling, right? You have quantization, you have discretizations, right? Then we spend about 2 weeks to talk about the difference equation, talk about the transform, right? Then last week we talk about the digital to analog conversion, about the coding, right? Then for the analog to digital conversion part, so we have to do sampling. Sampling basically got 2 parts. One is the discretization, one is the quantization. So for the discretization, basically you need to take care of our time, the sampling period or sampling frequency. So if your sampling period is very small, then you will see the gap between your analog and digital will be very small. But if your time period becomes bigger, then you will have some other issues. And we are going to further elaborate this P or the frequency at a later stage. Okay, we are going to talk about some of the aliasing issues and so forth. Another one is the quantization. Quantization means we are going to use certain digital memory to represent your data. So instead of infinite resolutions, okay, we have a finite resolution. So if the resolution is Q, then you may have this quantization error, okay, up to right? So Q is a quantization resolution, and the smaller the Q it is, you will see the smaller difference between the analog, right? And in this course, okay, we only pay much attention to this one. Okay, in this course, we assume except from the first chapter, okay, when we need to talk about the difference between the theta and the log sequence. Okay, we highlight. But later for the rest of the chapter, we only focus on this one, right? We only focus on this one. When you talk about differential equation or difference equation, the time cannot be zero, right? Then we talk about the Z transpose delay or the okay, we are not really paying much attention to the quantization in this module. Okay, but you need to bear in mind, this one may be significant. Okay, if your quantization error is not that small. So you see this one, you see we deal with the effect, okay, of the discretization only in the true Q. Okay, true Q is literally what means your quantity can be represented, okay, as good as your Q. Okay. And because the time issue, we have certain ripple effect and the lighting issue, and this one we are going to further discuss. Okay, most likely next chapter. And later for the introduction to the digital control, so basically we highlight the difference between your analog controller and digital controller. So you see this one, they are talking about how to sample your analog input by your sensor to a digital input. Okay? And now we're talking about how to convert or what the relationship with the controller side. What's the difference between your analog controller and your digital controller. Okay? So for the digital controller, instead of differential equations, we are going to do difference equation to do plus and multiplication. Okay. So we are going to do something called the numeric integration, and basically is something like sum up integration. So here we present what I say, okay? So basically you have three parts. N log digital, differential equation, difference equation, and then digital to analog converter when you are using the interact folder. So firstly, they introduce about Euler's method, okay, to do approximation from differential equation to difference equations. So basically, define the difference. Divide by the time period, divide by the time. Okay, so this is called the Euler's method, and Euler's method is overall, right? Depends on whether you're using the forward output value x in plus 1 minus your current value, or you look backward, use your current value minus the previous one. Okay. And after you apply this, eventually you are able to get difference equation. And based on the difference equation, actually you will come out with something called the recurrent function. That means I give you input at this point. Then you are able to calculate the output at this point. Then the output will respond to your basic words. According to your plan, you will have your next input. Once you get the next input, you put your next input value into your recurrence equation, you will get your next output. After the next output, you get the next input, you get the next output, next input. So you can continuous, okay, to do the real function. Okay. It also the same thing what most of the current controller has been achieved. Because you have a control, right? You are not going to tell the machine, or you are not going to tell the computer, I give you S, then you just control me, right? You are going to write certain programming, right? Or you write certain high level one, then you are going to convert into the actual programming control between your input sensor and your output, right? And how do you simulate the data? Right, and some of the in lesser space they will record some of the history data, they will also put data into. Then your computer will look at the sensor, will look at the memory, then based on the difference equation or recurrent equations, then calculate your output. Then the output will be sent to the actuator to control your motor, to control your engine, to control your heater, to control your fan. So eventually you're able to get the difference equations. So we also have done certain exercise how to convert the analog controller or analog converter to a digital one. Okay, or we present by difference equations. So the general process is if you are giving a S function, what you need to do is you need to expand the S function, okay, and take the one to use the S as an operator. Okay? And S operator is a differentiation. Right? S operator means differentiation. Then from your S function, you do the inverse Laplace transform, you will get your time domain, then you get your differential equation. Okay, you may have first order, you have second order, you have third order. Once you get the differential equation, then you can apply. Then you can apply the Euler's over approximations. And each approximation, you can approximate for one order of differential. So if you got first order is simple, it's like this. But if you got second order, then not. Second order is a differentiation of the first order. Right? So basically you need to apply the conversion. But in order for that to be applied one more time, you need some history data. Right? Instead of only UK, and UK minus 1, you need UK minus 2 as well. If you need to do third order, you need to have a UK minus 3 as well. Okay, so this is the reason in the teacher controls, you also need a memory. Okay, because you need to know what is the task. Okay, the higher order you have, that means the bigger the memory you have. Right? So we have done this one, so basically it's a commutator. Then we also try another exercise, which is a PID controller, right? So PID controller, at least you have a second one. So for the PID control, if you follow the sample exercise, they apply the numerals forward or backwards to approximate your differentiation. But if you have second order differentiation, then you need to 2 times. Right? If you have second order differentiation, you have 2 times. So you will notice for second order one, you have a k minus 1 and k minus 2, right? Because you have second order. So you need to have 2 delays, or you need to have 2 discrete data. And some students ask me a lot of questions regarding this one. Because basically for this one, if we follow the textbook, they use so-called the past data. So we estimate what is your current one, right? So that one is very logical. Because you have your past data in your memory, right? Then you want to calculate how much should be my current one, right? So that one related to your past output, related to your current input and your past input. So this is a difference equation. But some other textbook, you may also see something like this. Just to make simple, so I have a lot of constant to repeat as EPC. You may also see some of difference equations like this. And this one will be more used for so-called predictions. And mathematically, these two difference equations are mathematically, right? Because very simple. If I use some other variable, let me see j. Okay, let me see I use k equal to j plus 2. I substitute in, then what I get u j plus 2 equal to u j plus 1 plus some value a e j plus 2 some value e j plus 1 and some value e j, right? Alright, I just use j substitute in to get this one. Anyway, your j and k just represent your time, right? So if you want this two and k mathematically mean the same. But the only difference is in the real practice. For this one, you have your past data and you are calculating what is your current output, right? Alright. But for the second one, this one basically you need to shift your time. Okay, you need to shift your time. 2 steps. Right? And this one may be more used for prediction. Okay, so you need to predict. Okay? What should be confusion. But mathematically they're the same. One is you know all the the first one is more available for engineering, for your control purpose, because you know your input, you know your error, you know your input. But your sensor, you compare your sensor with your result or your target value, right? So this one is very straightforward. Okay? For the second one, Just for information only, it can be used for certain modeling and predictions. So if we predict, okay, what should be happen in the future. But you will notice here, if at the moment, if let me see the moment is 0, I only got this. I don't have this, I don't have this, I don't have this. So all the rest will be based on certain modeling and predictions. Okay, and the control will be more used for the observer. Okay, and the observer goal for the estimation of predictions. Okay, but in order not to confuse you, we can just think, okay, means what is original form. But for those students who want to know more, okay, if you read other textbooks, you will find some other definitions. Okay, then nothing to see must be this one or nothing to this one. Okay, you just because it shift the time a little bit. Okay, so some more use for the prediction. Okay, some more use. And after we get the difference equation, so basically we are able to get some of the concurrent equations. So based on this one, it means you have your current information from the sensor, you have your past data from your memory, then you're able to determine what should be your current output. And how can you obtain this one? This one is obtained by solving the so-called difference equation, right? If you notice, this one is just a general form of this one. So if in your exam asks you to do a linear digital approximation by unit over method, no matter what method they ask you, you should eventually come out a prediction of your current output, okay, as a history output, past output, together with your current sensor input and your past input. Okay. So this one on one side is something you are able to program. You are able to program it into your computer, into your microcontroller, then you achieve your control functions. Okay? So first of all, you get to know the engineering meaning of this one. Right? Because if you know engineering meaning of this one when you are computing, each one will be your variables or your tables for the data to be updated and the report. Right? And after you have all the variables, you are able to calculate what is your then your control system will be going to your real physics plan. Then you have a next process. Then you get your next input. Then you're able to calculate your next input. So first of all, you understand engineering meaning. Okay, this one is the thing for you to program, the thing for you to implement for your control. Another one is, if you have this one, I want to do certain analysis. Because I don't want to apply a controller data you make it unstable. You have it, right? So, on the programming side, on the application side, this one give you an equation which you have to program it. But before you program it into your real action, into your real control, you want to do certain analysis. You want to at least do certain analysis about stability, right? So how to do the analysis of stability? One way is you take this one as a difference equation, you will try to solve it. And so this is the thing we talk about how to solve a difference equation. How to solve a difference equation is something very similar as how you solve a differential equation. So you will present a general solution. And you substitute this general solution into your difference equation. Then you are able to get the root. And for this one is your solution to your simultaneous differential equation, right? And if you notice, and by today you should know, when you talk about the stability, it is something to do with your initial conditions. You do not necessarily solve the final solution of your difference equation. you only need to solve the simultaneous one, which you only need to get your Z1 error. Because this one, the location of this one will determine the stability. Of course, if you want, you can further solve to get the variance. Right? Because for your general solution, you have your root, you have your variance. Right? So this one can be your A1 multiplied with your Z1 of A plus A2 Z2 of A. Right? Or if you have third order, you have A3 plus A3 multiplied with Z3 of A. So A1 and A2 is essential, is important if you really want to solve the difference. Right? If this one is a math course, asking to solve the differential equation, you only solve the simultaneous one without the general one, I believe you will lose half. Right? For the control analysis, as long as you solve the Z1, Z2, then you should be able to determine the stability. Because the stability will depend on where your root will cut. If within the unit circle, it's stable. If outside the unit circle, it's unstable. And the condition should be all the roots within the unit circle is stable. Any one outside the unit circle. So for this one, if you notice, there is one which is outside the unit circle, then it's unstable. And how do we know whether it's outside or not? If you got a complex number, how should we do? You should calculate the length. You calculate the radius. You should use your imaginary class square plus your real class square. This is something you already know, right? So if you have a root A plus JB, so you need to find out what's the magnitude. The magnitude is A square plus T square. Right? So you need to check this one whether this one is greater than 1, equal to 1, or less than 1. Okay? So after we talk about the differentiation, then we talk about the integration. Differentiation is approximated by difference equation. Xa plus 1 minus xa. Then your integration will become a combination. Will become a summation. So if your output is an integration of your input, then basically you can use similar things like forward rectangular, backward rectangular, and category. Okay? So this one is how to do the approximation. Because the actual integration is supposed to be later. Right? This should be your actual one. But for the approximation, because you can only handle summation and multiplication, so what you can do? You either form a rectangular or you form a category. If you look forward, then this is a forward one. If you go backward, this is a backward. Right? Forward, then this one is backward. Then this one is a you also have backward. And now if you notice, this one is also represented by some of the difference equation here. Right? Because the difference between your UA and your UP minus 1 will become the value. So you see, if you present this one, is your integration, right? If I present this one, is what? This one is what? This This one is your differentiation. And this one is your backward differentiation. Right? Is it backward or forward? Forward, right? Because here your input is k minus 1. If you shift everything by 1, you get the ek equal to k plus 1 and ek equal this. This is for forward. The Euler's, right? Your Euler's forward, right? So you see this one, your Euler's forward and your forward rectangular means the same thing. This one is your rectangular, right, for integration. But actually they are the same thing. It's just whether you want to put the input as a, sorry, your output as a function of input. You can make the integration, right? Because for this one, your output is an integration of the input. Their input is this is two equivalent? Almost. When this one be equivalent? If your initial condition is 0, right? If your initial condition is 0, this two will be equivalent, right? Alright. If all your integration up to 0 is 0, right? So you see your backward, forward, Euler's one for differentiation, actually is the same for your forward rectangular and your backward rectangular. Okay? And similarly, you can also try this one. And later we also have one exercise in exercise 4. Okay, so after we introduce about the difference equation to approximate integration as well as the differential equations, right? Then we finally introduce the Z transform. In your Laplace, you got in your continuous domain, you got the Laplace transform. So eventually you got your S function as a transform function. So similarly, in the digital control, we have the Z transform. Okay? So the Z transform compared with the Laplace transform, they are very similar. The Laplace transform, what you need the integration of your function multiplied with e power st. Right? When you s from the infinitive to when you t from your negative infinitive to the positive infinitive, right? But here is the same thing. But instead of integration, because in linear control we have no integration, what we do summation. So you have this sigma. Sigma means summation. And you multiply with z power minus k, right? So what we can do is, once you get the difference equation, you can do the Z transform. After you get the Z transform, then you are able to convert your time delay. After you, for example, here you see you have a time delay, you got k, you got k minus 1. Right? If for other more complicated, you can use k minus 2, k minus 3, k minus n. Right? So if you have n delay, you will have n variables. Then it may be very difficult for you to visualize, very difficult for you to do analysis. Right? Because you have so many independent methods. But after you have done the Z transform, how many variables you have? If for this one, after you have done the Z transform, how many variables you have? You get the Z function, right? Z function is what? Z function is function of Z. Right, function of Z is what? Z is a variable. You only have one variable. So instead of n variables, now you only got one variable. Okay? So after you have done the Z transform, you only get one variable, but all the time delay become a Z power minus 1, Z power minus 2, Z power minus 3. Okay? Then you can obtain or you can get a polynomial function with only one variable Z. So now if you think about your Laplace transform, what Laplace transform means? You got higher order, right? You got first order, second order, third order, fourth order, fifth order, nth order. After you have done the Laplace transform, what you get? You don't have that much order of differential equation, but you get certain order of polynomial functions. Z transform, similarly. Before the Z transform, you got 1 delay, 2 delay, 3 delay, 4 delay, n delay. You got 8 delay appear to be n independent. Okay, that is very difficult for you to solve. But after we obtain the Z transform, instead of so many time delay, so many independent time delay variables, we only have the Z variable. We convert all the time delay into polynomial functions. So you see any back shift represent Z power minus 1. Of course, any forward shift will be power Z. So after you get this, you get something called the transfer function. After you get the transfer function, you can use the transfer function characteristic equations to represent the system. Then you can evaluate where the loop is. You evaluate the system visibility, we evaluate the system response. So similar as what we reviewed just now, you also have the form and 0 form. Then you are going to do certain analysis from where the most in the complex form. After you get the transfer function, you can also have similar things as the clock diagram, okay, as your previous one. So we also did certain exercise, okay, how to represent a difference equation or a Z function. And after we get the transfer function, the next step, similar as the value control, you are going to do the response, right? The input output. So the first one, the most important one is the impulse. So we have the pulse response, unit pulse response. So for the unit pulse, you only have your input and the initial rest of the time. And if you do the Z transform, the good thing is for the pulse response. For the pulse inputs, the Z transformation is 1. And if your input Z transform is 1, then your output response is equal to your transform. So this is also the way to link between your signal and system. So if you give the pulse response, that signal, that output signal, basically is quite the signal. Okay. And similar as the Laplace transform, you also have the convolution. What the convolution means? Because your final output by right should be your Z transform of your input multiplied with the Z transform function of your transform function, right? So if you, according to the definition of the Z transform, this is your definition of the Z transform. If you're according to the definition of Z transform, you put this one to here, put the transform function here, you are supposed to get, this is your input. This one is your output, right? According to the definition. Then you apply very simple mathematics application, you extend it, you get this one. And remember, there are certain meaning about the order of the Z. They are corresponding to the time delay. So which means this one should refer to your U0. This one should refer to your U1. This one should refer to your U2, and so on. Then if your output is supposed to be a recurrence equations, your output, as what we described before, it should be certain calculation, certain function between your past output and your past input and your current input, right? So this one should be a final solution, right? So if you do the mapping, you will notice your U0 is equal to this one, U1 equal to this one, U2 equal to this one. Because don't forget, your UZ is also a Z transform of your UK, right? If you do the Z transform UK, you get this one. So they must have a certain mapping, right? So this bears the convolution path. So eventually, for each of your UK is corresponding to the discrete convolutions. And based on this, if our input is a unit pulse, if the input is unit pulse, what do you think? If the input is unit pulse, only when your J equal to 0, you get 1, right? The rest is 0. So what you get? UK, you get HK. You got it? If your EK is an impulse function, if your EK is your impulse function, then your UK for each one will just be HK, right? Okay, pay attention. This is not UZ equal to HZ. It's your UK will be equal to HK. Why? Because if J does not equal to 0, it's 0. Only when your J equal to 0, you get 1. When your J equal to 0, you get HK. So this value is just equal to HK. Alright. So if we do the impulse response to the unit impulse response or the pulse response, we can check the VIBO stability. The VIBO stability means if your input is bounded, as long as your input is bounded, your output must be bounded. Okay, bounded means you have a boundary. You have a maximum value. You are always less than a certain constant value. Okay, you are always less than a certain finite value. And how to do the checking? Okay. The checking is you want to check and you want to make sure the summation from your HK from the negative infinity to the positive infinity, you sum up everything together. This one should be bounded. And just now we review the pulse response. Each UK is just equal to HP, right? So they need all the summation of your pulse response to be bounded. Okay? So the condition is the infinitive summation of your pulse response to be bounded. It's not your pulse response to be bounded. It is all the summation. Okay? So we have studied this one with the trapezoidal. For the trapezoidal one, the impulse response, then your k goes to infinite. Your system still constant as speed, right? You have a bounded output if your input is a pulse. But if you sum up all the U1, U2, U3, and here U infinity, or H0, H1, H2, H3, go to H infinity. You add up everything, you will get infinite. So your PIPO stability, let me highlight as the last time, is not to check. Is not to check whether your H infinity or whether when your k goes to infinite is bounded. It's not check only this. Okay, it's not only this. It's to check all the summation where your k and your negative infinite is the positive. So this one is only one value. You need to sum up. Okay, you need to sum up everything. If you sum up everything, you get bounded. That is. So a very clear case, you have this one equal to 1, as long as not 0. You do all the summation. You have HK here. You do all the summation from the k 0 to infinite. So most of the time we will assume is a non-partial scenario, which means all the paths before the initial condition is 0. Okay? This one will be infinite. So it's unequal solution. Okay? So your PIPO is must check all the summation from your initial state to the infinite state. All the values add up. Okay, all the values add up. If that one is stable, if that one is converged, if that one is constant, then your PIPO is stable. It's not to check when your k goes to infinite. It's not only to check the final value. It's to check all your values from the initial to the final. Everything starts up together. Is that right? So actually for all the integration, no matter whether you are using backward, you are using forward, you are using trapezoidal, the PIPO should be unstable. Right? Because every time you integrate, you get one value. You have the infinitive add up together, infinitive 1 is infinite. So how to do the PIPO checking? Then you get to give an impulse response. So you get to give a pulse response. After you get the pulse response, you get your output. Then you add up everything. Then you look at the stability. And usually this one will give you an infinite time series, which usually is a geometric series. Okay, usually it's a geometric series. So this one is something you have to do. You have to look. If let me say I have 1, I have an A, I have an A square, I have A cubic, A mountain, and so on and so forth. If you want to do all the summation, it's not just to pass first, second, or third one. You have to sum up everything. And this one should be 1 over 1 minus A. Condition is A, or the magnitude of A should be less than 1. If this A is equal to 1, you sum up what you get, infinite. If A is greater than 1, you get infinite. Only when your A is less than 1, then you have a constant value, which is 1. Okay? Of course, in the real engineering world, not necessarily everything give you a good geometric series. Okay, but most likely in your exam, if there's some questions, give you an example. Because those is something I think you have done so far, you're able to get the summation for infinity of terms, right? This one. Have you ever learned other series? Other infinite series which you are able to do the summation? Any other things you have done? Alright, but this one you should be related, right? Yes or no? Okay, so we talk about stability. I do hope now everybody are very confident of that. So you have to do the pulse response. After that pulse response. Okay, and the last thing we have done so far is the holding. So we have the input, then we use the 0 order, and this one is corresponding to the digital to analog converter. So if you still remember, for this distance, we cover the sampling, we cover the difference equation, Z transform, then we cover the holding, right? And the digital to analog. So for the 0 order holding, basically you hold, so this is your time equation about the 0 order hold. You hold for 1 period. So this is 1 minus 1 period. Okay, 1 period. Because you holding only hold 1 period. And you do the Laplace transform of this one, you will get this one as a Laplace transform. And because your digital information, which is UK, comes to the 0 order hold, then comes to the analog pair. So these two are both in the analog domain. So if you have a function, S function, and here you have a GS, because the block diagram, the basket one, you're able to just classify, right? So your total one will get this one. Okay, this is the meaning why you can do the multiplication. And later what you have to do, because here you will get your output already, which is your ET. So later based on the ET, you are going to do the sampling. Okay, or your analog to digital. So now in order to do this sampling, you need to convert your analog to your digital, right? Or your continuous time to your digital time. So you are going to do your Z transform of this. So actually you are doing the Z transform of this one. And let me highlight one more time. No matter in the Z transform or in the Laplace transform, please, ZA plus ZB is equal to ZA plus ZB. That one is correct. This one is correct. Because Z transform, Laplace transform is a linear transform. For the linear transform, you have the superposition. But superposition, the super only apply for plus minus. Alright. This one is true. If this one is not true, there's something wrong with it. Okay, then your life will be very tough for you to do the inverse Z transform or inverse Laplace. This one is true. But is this one true or not? Why is it not? This one is not true, Be careful, this one is not true. Okay? Because I received some email from some of the students show me different solutions, get different ways. And basically what he or she did is, for example, I have S plus 1 squared. Right? If I want to do the Z transform of this, how can we do? The students say, hey, if I do this, I do this one first, then I do this one first, then I get different answer. Even I refer to people are different. All are different, because this one. Why? Very simple. If this one is true, ZA times 1 is equal to ZA. Yes, right? Like is equal to ZA times Z1. No, right? If it's 1, you have another one, right? Alright. So you just use this one to see this one is not true. Okay, and don't confuse yourself. So what you need to do, if you get some high order, for example, in your exam, if you get some high order, if let me see have this one, how you do the transform? You don't, please don't try to do this. Don't try to do this. Don't always copy A. Or better do this. Okay, copy that. And please copy that this carefully. It's not. What you need to do, if you want to do is S plus 1 minus S plus 2. Do the factorization. Right? If you done the factorization, you look for this one, you minus. Now is it true or not? This one is correct. Okay. So that's the reason when you learn your dynamics calculus, you need to do a lot of factorization, right? Right. Alright. Because your factorization will get something in plus or minus 4. Then you're able to look individual one. Right? Then you're able to look at this one, you're able to look at this one. You may not be able to find the table for this one. You may not be able to find the table for this one. But you may be able to find the table for this one, this one. Right? So you need to learn something about factorization now. So basically the zero order holes, the motion is very straightforward. Okay? Your zero order holes, the packet hole is 1 minus e power minus st divided by s. So you can do that one. And also please pay attention that this one becomes this, I think I explained last week. You multiply with this one is not because of this one. It's not because of the second law. This one is this one. It's not. Is they have done they convert this one, and this one will become and this one becomes because this is candidate. Then they combine. They still apply the superposition, okay, the plus minus, not because of production. Okay. So that's what I highlight. So this is something actually we showed last week. And just look at the slide. Nothing new for today, right? Okay, and the last thing, okay, we are going to finish this one, then we have a break. So for this one, the last thing they are talking about is the Glasgow flows. We talk about the other response. Because now we talk about the pulse. Right? We also have the unit pulse, we have the unit step, we also have the sine cosine. So this one they are able to represent by different Z functions. So the unit pulse, Z function is 1. The unit step, the Z function is Z divided by Z minus 1. And the displacement function is just Z over by Z minus R. And R is a radian, is a phase. And sine, cosine. And actually, this one's supposed to be cosine. Okay, sine not be cosine. And you get the Z transform in this one. And for different functions, okay, they have a different positions. For the unit step, if you look at the code, for the unit step, this one is at the positive one, at the edge of the unit step. This one is at R. If R is less than 1 is stable, if R is greater than 1 is unstable. Okay, so it depends on where your R is. Okay, this one tells you where the root is. Okay? And for your sine, cosine, again, this is where the root is. And basically, the magnitude in R, and the fixed angle is plus and minus theta. Okay, basically, this tells you where the root is. Okay, if you look at the column. So finally, they are talking about the frequency. So your general solution, after you go to the time domain, you get this one. And actually, your R, you can represent this one with your R, and this one becomes RK. And use this one to be your CR, become cosine RK. That means actually your position of your poles is corresponding to your radian R and your theta and the angle theta. And you can do certain comparison between your Z domain and your continuous domain. Okay. And this one we spend about 1 week, right, to see how to map into the Z axis. Okay. And I think this one is something you're very familiar with. So this is they have armor corresponding to the next node of the glass cosine. Okay, so this is the last page. We are going to cover by next week. Next week we are going to talk about see what will be about the okay, so let's have about 5 minutes break. Okay, then we'll go through some of the highlights